I'll now a short lesson conduct on a new math lesson instruct. Whether you push or yank, the torque on a crank comes from a vector cross product. In this chapter, we will look at a review of bicycle and wheel linear velocity, torque as a vector cross product, and crank torque angles in pedaling. Watch the graphic of the wheel on the bicycle and the wheel separate as we roll out one revolution. We will let D with the tire be 660 millimeters. That gives us a diameter shown here, an equal diameter shown here. So the circumference is pi times the diameter, which is that. And when I multiply that all out, I get about 2 meters. Bicycle moves forward 2 meters at the same time that the wheel rolls out 2 meters of circumference. Here is our rider, and let's assume for a minute that he's able to put all of his weight on his right foot on the right pedal. Then I would have on that pedal a force equal to his mass times the gravitational constant, and that causes a torque on the crank, and that causes a torque on the rear wheel, and I get the bicycle accelerating according to force equals mass times acceleration. But the entire weight of the rider is never on the pedal because there are forces between the foot and the pedal that are quite complex and involve the biomechanics of many muscle groups in the legs and back and large changes of angles in the hip and knee joints. I'm nevertheless going to simplify the calculations and idealize the discussion as if he can put all of his weight on one pedal. When his foot is contacting the pedal, when the pedal is at this position, he can apply some torque. When the pedal is down here, on the other hand, and the force is straight down, then there's no torque. We're going to look at some graphs and get to understand that very thoroughly. We're going to look at this part of the graphic specifically and see how it is that the position of the crankset provides torque to the wheel. For my bike and rider, I have a total mass of 100 kilograms, and that is made up of a mass of the bike of 10 kilograms and a mass of the rider of 90 kilograms. When all of the rider's weight is on the right pedal, then the only propelling force is the product of 90 kilograms times 9.8 meters per second squared, and that gives us 882 newtons. Here's my crankset. Here's my 90 kilogram rider. I have a crank arm length of 170 millimeters or 0.170 meters. There's my crank length, and I'm assuming that I can put the total weight of the rider on the pedal, exerting a downward force of 882 newtons, and this line here is the vertical bisector of the crankset. Here is our force, and that is the length of the arm, and that length of the arm is R, and R operates within this circle. The torque at any point for angle theta, theta being the angle between the crank arm and the bisector, is going to be equal to the vector cross product of R cross F, and that is equal to R times F times the sine of theta. So for any angle theta, the torque is 0.017 meters times 882 newtons times the sine of theta. So as an example, here we see the angle theta, and the torque at angle theta is equal to 0.170 meters times 882 newtons times the sine of theta. Here's the sine wave, in this case showing 2 revolutions. In the first 2 quadrants of each revolution, the sine is positive, and the third and fourth quadrants, the sine is negative. but my torque is always positive, so I'm going to plot a graph of the absolute value of the sine of theta. We're going to plot some values for torque on the y-axis as a function of the angle in degrees on the x-axis, and for any point on that curve, the torque at x degrees is going to be equal to 882 newtons times 0.170 meters times the absolute value of the sine of x. If you're a little confused by this setup diagram, the following examples will make it very clear. At 0 degrees, my sine of theta is 0, so I get a torque of 0 Newton meters. At 30 degrees, 75 Newton meters. At 60 degrees, 130 Newton meters. At 90 degrees, 150 Newton meters. At 120 degrees, 130 Newton meters. At 150 degrees, 75 Newton meters. And at 180 degrees, my sine is again 0, so I have no torque. Now my left crank takes over, and at 210 degrees, I have 75 Newton meters. At 240 degrees, 130 Newton meters. At 270 degrees, 150 Newton meters. 300 degrees, 130 Newton meters. 330 degrees, 75 Newton meters. And back to 0 Newton meters, this time with the left crank all the way at the bottom, and we have completed one complete pedal stroke. Let's see it with a little motion, and as the crank on the right turns, you'll see that red line sweep across the graph. With clipless pedals, you can even this out quite a bit, but it's still true that as the cranks turn, there is a constant change in the amount of torque that's transferred as well as power transferred to the rear wheel.